Now it is started. Okay. So we were discussing what we discussed last time. We started with the introduction of the uniprocessor scheduling, where we discussed different types of schedulers. Okay. Do you remember the different types of scheduler that we discussed? Can anyone tell me broadly what were the topics that we discussed last time? Okay. Uh, Let me remind you what we discussed mainly. That was types of scheduler, where we discussed long time scheduling. Yes, mid-term scheduler and short-term. Correct. Not exactly IO scheduler, because IO scheduler is yet to be discussed when we will discuss IO part. And then we reduce our talk. Then we narrowed down that throughout this chapter we'll be discussing various short-term scheduling strategies, because long-term and mid-term they are also concerned with the memory part, whereas short-term scheduling that we are actually discussing in this particular topic, they are mainly dispatching techniques or dispatching strategies. So whenever there is a time for OS to decide which process will run next, then dispatcher comes into the picture, and that is the strategy which is used at that time, that is called short-term scheduling strategy. And today we will be now starting with different or the various scheduling policies. Now let me tell you one thing. If any one of you are going to take GATE exams, okay, if you are going to give GATE exam after this is very important topic for the GATE exam itself. There are questions which are asked based on this scheduling strategies. So in that sense also this is very important. And again, this is interesting because now we are going to do little bit maths. There will be some problems that you are going to solve. So this is not pure theory in that sense. So I hope you will enjoy this part. So which are the various scheduling policies that we are going to discuss? So these are the strategies: first come first serve, round robin, shortest process next, shortest remaining time, highest response ratio next, and feedback. We'll see how many we can do today. We also discussed a little bit about the selection function. Uh, Selection function is a function which determines which process is selected for execution. So on what criteria the process will be selected for the execution. The function may be based on some priority or based on some resource requirements or the execution characteristics of the process. So basically, in all these various strategies, what is the base to decide that which process will run next? That base is nothing but selection function. And some of the terms that we need to be aware of: W, it is showing the waiting time, that is the time spent in the system so far. E shows time spent in execution so far, and S, total service time required by the process. Then there is a term called turnaround time, which is one, I hope you remember last lecture. This turnaround time, it is one type of criteria to measure the performance. So turnaround time is nothing but the total service time required plus waiting time for that process in the system. It can also be calculated using two other quantities, that is finish time minus arrival time. So this turnaround time is also can also be calculated as finish time when it gets finished minus when it arrived. So that is arrival time. Then there is another term called normalized turnaround time, which is TR by TS, where TR is nothing but turnaround time and TS is nothing but the total service time. Okay. And this normalized TAT, that is turnaround time, it gives you relative delay experienced by a process. So when you want to compare two processes based on turnaround time, normalized TAT is the better quantity or better measurement that you should use to compare those things. We will see today. And then we also discuss decision mode. So it specifies the instance in time at which the selection function is exercised. So it is the instant of time when this selection function is used to decide which process will run next. Now this decision mode, okay, it is of two categories: non-preemptive decision, non-preemptive and preemptive. So what is non-preemptive? Once a process is in the running state, it will continue until it terminates or blocks itself for IO. So if your strategy is to use non-preemptive mode, then once a process is scheduled and it is executing, it will not be interrupted. It will not be rather preempted. It will not be forcefully removed from the processor. It will continue until it terminates itself because it has completed its job, or it blocks itself because it is waiting for some IO or some other event. So that is non-preemptive strategy. And another category is preemptive, where currently running process may be interrupted and moved to the ready state by the operating system. Why so happen? So preemption may occur when new process arrives on an interrupt or periodically. Okay, and when this preemption happens normally, so this preemption may occur when the new process arrives in the system, okay, or when there is some interrupt, or periodically this preemption can be performed. So depending on the strategy that you are going to use for scheduling, short-term scheduling, preemption, different types of preemption can be used. So we'll see that also. And there is one question, that which decision mode should be preferred, preemptive or non-preemptive. So normally preemptive mode is more preferred. Why? Though it may increase overhead, that is for sure, because preemptive means what? The running process will be preempted and it will be removed from the running state and put into the ready state. Maybe though it is able to run, we are still removing from the running state. So of course it is going to increase overhead because number of process which will increase. So overhead will increase, but then it prevents one process from monopolizing the processor. Just assume that there is one process which is going to take very long time, and it is not going to perform any IO. It is purely CPU bound process. So if you are using non-preemptive mode, so that long process will continue to run for maybe for days, let's say. So in that case, the processor will be used only by that process and other processes will never get chance to run. So that is called monopolizing the processor. So in such cases, it is always better to use preemptive mode. I hope you are getting this idea, the preemptive and non-preemptive. Please let me know. Yeah. Okay. So let us start with the first strategy. First come, first serve, the simplest one. We can also call it FIFO strategy. And that is normally the most fair strategy in real world. This is the most fair strategy in the real world. If you come first, you get first chance. Simple. Okay. But though it is most fair policy or strategy in real world, it may not be the most useful in case of OS. Let us see what is Fcfs. So normally there is a ready queue, and whenever new process comes, it joins that ready queue at the end. When the current process ceases to execute, okay, if current process is now, maybe let's say it has completed its job or it is blocking itself, the process which is waiting for the longest time in the ready queue is selected. Does this make sense? If you have a queue, okay, which process in the queue is waiting for the longest time? What do you say? Yeah, the one that came first. The one that came first is waiting for the longest time. So in that sense also you can say that this is the selection function. Selection function is max of W. W is the waiting time basically. So maximum waiting time, the process which has maximum waiting time, that will be selected next. And this decision mode for this strategy is non-preemptive. Fcfs works in non-preemptive mode. It means once a process is scheduled, it will be running until it completes its job, or it blocks itself for waiting for when it is waiting for some event. Otherwise, it will not be stopping and it will not be ceased to execute. So let us see one simple example. So this is a set of processes A, B, C, D, E. These are the processes, and these are the arrival time when these processes came. A, it was there at the very start, so that's why arrival time is 0. At time unit 2, B came. At time unit C, 4 came. At time unit 4, C came. At time unit 6, D came, and at time unit 8, E came. And these are the service times required. These are the service time required for every process. Process A needs 3 time units to be completed. B needs 6 time unit to be completed, and so on. In some, what do you say? In some other literature, instead of service time, you may be given CPU burst time. You may be given CPU burst time and IO burst time. Okay, first of all, let me ask you one thing. Are you aware of this term called CPU bound process and IO bound process? Have we ever discussed that? Please let me know. Do you know these terms called CPU bound process and IO bound process? Okay. So Ayushi says that we discuss it. How about others? Let me brief you again. What is CPU bound process? See, normally a process, it runs when it runs on the processor. Okay, so whatever time it for whatever time it utilizes the processor, that is called CPU burst time. And the same process where it is doing some IO and waiting for that IO. So for whatever time it does that IO, then it is called IO burst. Okay. Now the process, let's say some process, you have written a program which does lot of calculations, but it is not interacting much with any of the IO device. It is not taking any input runtime from the user. It is not showing any output to the user at the while it is running. Only thing is, when you start that process, at that time some input is already submitted in that program, and at the end, after performing all the calculation, it will simply produce the output. So if you talk about this kind of program, when you run that program, most of the time it is doing some calculations behind the scene, and it is not performing much of the IO. So the most of the time of this process, it is going to use CPU rather than IO. And that is why this kind of process is called CPU bound process. So the process which spends most of its time by executing on the processor, then it is called CPU bound process. If a process is spending most of its time while doing IO rather than doing much of the calculation, it is spending most of its time while doing some IO, then it is called IO bound process. Does this make sense? So what can be the example of IO bound process? What can be the example of IO bound process? Writing data to a file, fine, that can be considered. But see, once it gets that IO device, then it won't be doing much of it, right? It is simply transferring the data up to a certain extent, fine. But visualize the process like where you are doing some chatting. You are doing some chatting. Okay, most of the time the process is waiting for some input from the user and to display it to the user, isn't it? It need not to do much of the calculation, it need not to do much of the CPU processing, right? I mean, most of the time it is doing some IO. Sorry, I'm not getting this answer. Rate of process, what are you trying to say? Rate of process, can you elaborate on this? If you want, you can unmute and you can speak, no problem. Rate at which a process forward. Still, I'm not getting it. Fine. If you want, you can please elaborate that by unmuting yourself, or otherwise I'll go further. Okay, fine. Defragmenting a hard drive. Fine. Yeah, you can say that. Okay. Let me. Yes, you can say in that sense also. Someone was saying that writing data to a file, reading data from a file and displaying it to the terminal. Correct. All these are IO bound process, because they are spending its time in doing some IO, defragmenting a hard drive. Fine, you can say that. That is also one kind of IO bound process. Correct. But in that, normally it is happening behind the scene. Once it gets that IO device, now continuously, most of the time we have DMA for this, direct memory access, DMA controller. Are you aware of this? Have you heard this term called DMA, direct memory access? There is some circuit in the it's a hardware which once gets some IO device, let's say a hard drive or something like that, then through DMA all this data transfer happens between your system, between your RAM and your hard drive. So that is there, fine. But that is, of course, you can say that that process is mostly spending its time in IO. So you can consider that as IO bound process. So now let us concentrate on this example. So this is one set of processes. These are the arrival times of that process, and these are the service times. So just do some calculus, small thing here. Can you tell me which process will be executed first? Which process will get the processor first? Definitely A. Okay, definitely A. And when it will complete process A at 3, yes, at 3, correct. Then which will process run next? Which is the process which will run next? B. Okay, and when that will complete 9. So you understood the idea, right? So at time 0 there is only one process in the queue. This is my ready queue. This is my ready queue. Okay, and this arrow shows which process will run next. So A will run next at time 0 because there is no other process. At time 3 that will be completed, and at time 3 there is now only one process there in the ready queue, that is B, which arrived at time 2. So it will run next. But while this process B, it will complete at it starts at time 3 and it ends at the time 9 because it requires 6 time units. While it completes, now there are 3 processes in the queue, ready queue, C, D, E. Based on arrival time, we put it in the queue. So at time 9, which process will go next now? Which process will go next? C. Simple, right? And when it will be completed? Correct. So it will be completed at 13. At 13, D will go next. And when it will be completed? 18. Correct. And then finally at 18, E will go next because that is the only process, and it will be completed at 20. Simple. So at 20 now your ready queue is empty. Okay. So you can think this way also. So A goes from 0 to 3, then B goes from 3 to 9, C goes from 9 to 13, D goes from 13 to 18, and E goes from 18 to 20. So this is the simplest example of FCFS. Okay. And if we calculate turnaround time, the turnaround time can be calculated as finish time minus arrival time. So turnaround time for A is 3, for B it is 7, for C it is 9, for D it is 12, and for E also it is 12. So these are the turnaround time, which is one performance measure, which is a performance measure. And for a better performance, what do you think? What should be the value of turnaround time quantity? High or low for the better performance? Low. It should be low. Correct? So you can see here the same example. Okay, finish times, turnaround time, and then there is normalized turnaround time. Now normalized turnaround time is the turnaround time divided by service time. So 3 divided by 3 it is 1, 7 divided by 6 it is 1.17, 9 divided by 4 2.25, 12 divided by 5 2.40, 12 divided by 2 6. Okay, and these are the mean values, mean turnaround time and mean normalized turnaround time. Mean is another, you can say, this mean value gives you some picture related to the set of processes. So mean turnaround time is 8.16 and mean turnaround normalized turnaround time is 2.56, and this is quite high. Especially which process is going to face highest delay? Can you tell me? Which process is going to face highest delay? Yes, E, because normalized turnaround time, it is 6. So it is a relative delay, right? Normalized turnaround time is a relative delay. Relatively, which process facing the highest delay? That is 6. I mean, that is E because it is 6. And then D. Then after D, then after C, then after B, and finally E. This delay is cannot be considered as delay actually, because that is same as service time. Turnaround time is same as service. So 1 is the best value. Okay, can we have less than 1? Can we have less than 1 value for normalized TAT? Yes, can we have less than 1 value for? Not possible. It is not possible. When it can become less than 1? When service time is more than turnaround time. Is that possible? The new denominator is more than numerator, then only it can be less than 1, but that is not possible. Service time cannot be more than the turnaround time. So 1 is the best value, you can say, right? Now, so there are some issues. Okay, there is a question, sir, as it is FCFS, can we say that the delay will be most for the process which entered last? Okay, just wait for some time. Let us discuss this issue and then you will get the answer. So issues with FCFS. What are the issues with FCFS? First, a short process may have to wait a very long time before it can execute. Okay, what does this say? A short process may have to wait a very long time before it can execute. So what do you understand by this? It is possible that when short process enters into the system, before that there are few long processes. There are few long processes in the queue before that process. Okay. So let us see one example. Again, there are four processes W, X, Y, Z. Arrival time is 0, 1, 2, 3. Service time required 100, 1 and 100. These are the service time required. So X and Z, they are long processes. W and Y, they are short processes. Start time for W is 0 because that is the first process. And it requires only one time unit to be completed. So it will be finished at 1. So turnaround time is 1 because it is turnaround time is finish minus arrival. So it is 1. And normalized turnaround time is 1 by service time 1. So it is 1 again. So for W, it is very simple idea here. It is going smooth for W. Then X comes, which starts at 1, which comes at 1, which starts at 1, and it is going to run for 100 time unit. Now you just see here, when X started, it started at 1. And at time unit 2, Y already came. Y already came. But before that, X was there and it was running, and it is going to take 100 time unit. So Y came at 2 and it gets its first chance to run at 101. It came at 2 and it is going to start at 101 time unit. Okay. So what is turnaround time for Y? 100. It is same for X. But for X, what is normalized turnaround time? Only 1. Because that is turnaround time divided by service time. So 100 divided by 100, 1. Whereas here it is 100 divided by 1. So it is 100. So for Y, you can see that for shorter processes, FCFS can be a problem. It may have to wait for a long time. And for Z, which is a long process, now again you see Z, which came at 3 and it starts at 102. Okay, but still its normalized turnaround time is only 1.99, which is comparatively very good. So here, which process is a victim of this strategy? Y. Y is a victim. Okay. So normalized TAT for Y is 100 times the service required as per this example. So in this example, it shows that a shorter process may have to wait for a long time before it can execute. That is a possibility. So that is one issue with FCFS. Has that answered your question? Someone asked some question. Okay. Now, another issue with FCFS, it may favor CPU bound processes. Now, favor means what? It means it is going to give more time to CPU bound processes rather than IO bound processes. So I just discussed what is CPU bound and what is IO bound process, right? So what happens in case of IO bound process? Let's say IO bound processes have to wait until CPU bound process completes, although being in a ready state. So what this says, let's say you have a good mixture of this IO bound and CPU bound processes in your queue. Whenever CPU bound process is a process which spends most of its time while executing by the processor, right? So what happens? That process, as this is non-preemptive strategy, once it gets a chance to run, once it gets a chance to execute, it will continue for a long time. Okay, let's assume that we have such CPU bound process which does not do any IO. Just assume that, but this may not be the case every time. CPU bound process may spend some time for IO, but let us assume that the CPU bound process that we have in our system currently, they don't do any kind of IO. So whenever they get chance, they will complete themselves, right? Before that, they are not going to release the processor. And the IO bound process, what it does, whenever it gets chance to run, it will run for a very small amount of time, and then again it will be blocked because it is doing it wants to do some IO, and it will be blocked. And let's say it wants to do some IO with hard drive. So it will be blocked for a while. For a while, it will be blocked. But let's say hard drive is accessible and it is not busy. It is free. So immediately that block process, which was waiting for hard drive, and hard drive is becoming available, immediately that block process will join ready queue again. Yes or no? It will join ready queue again. Are you getting? Yes. Are you getting what I'm trying to explain? Am I audible? Okay. So what happened? The IO bound process, which executed for a small amount of time and block itself, but again it becomes ready and it will join ready queue at the end. And when it joins ready queue at the end, before that there can be more CPU bound processes. So what is happening here with the IO bound processes? They get small amount of time of the processor, they blocks itself, though they become ready again very quickly, still they will get their next chance after a long time. So most of the processor time will be utilized or will be used by CPU bound processes, and IO bound processes, they will be delayed and they will get delayed. Okay, it will take more and more time for IO bound process to complete its job. Does this make sense? Does this make sense, guys? How this FCFS schemes, it favors CPU bound processes, because most of the processing time or processor time will be utilized by CPU bound processes rather than IO, and IO bound processes will be delayed. So these are the two issues with FCFS. One is short processes may have to wait very long time before it can execute, and it favors CPU bound processes. So these are two issues with FCFS. So what we can conclude for this FCFS? FCFS is not an attractive alternative in pure form. If you use FCFS like this in pure form, it is not an attractive alternative. It can be combined with any other schemes to achieve the benefits of both of the schemes. We will see FCFS will be combined with some other schemes. So there is one example, FCFS combined with priority scheme. Now you can combine this FCFS with priority scheme. Different queues for different priority levels. Each queue dispatches process based on FCFS. So now there are multiple queues and each queue is operated based on FCFS. That is FIFO, normal FIFO. But then every queue has its own priority. And based on priority, the process from that particular queue will be selected. So here FCFS, which is combined with priority scheme, can be more useful than the pure FCFS. And we are going to see one of such schemes called feedback queue. We will discuss that. We will discuss that, one of such schemes called feedback queue. Does this make sense? Please answer, please reply. Are you getting? Yeah. So can you very quickly do this example? Can you find out finish time, turnaround time, and normalized turnaround time for each process, and mean TAT and mean normalized TAT? Do it very quickly. Let me see how fast you can do it. Yes, anyone? Finish time for A is 3, okay. For B it will be 8. For C it will be 10. For D it will be 15. Simple. So finish time is very simple. Turnaround time is, for A it is 3, for B it is 7, that is 8 minus 1, 7. 10 minus 3, 7. So C is 7. For D it is 15 minus 9, 6. Correct. And for E it is 20 minus 12, 8. Okay. So turnaround time is correct, right? So mean turnaround time is 6.2. Fine. I'm not calculating. I'm just trusting on you. That is 28 plus 3, 31. 31 divided by 5. Yes. So that is 6.2. Correct. So mean turnaround time is 6.2 and mean normalized turnaround time. Someone has already given the normalized turnaround time. 1, 1.4, 3.5, 1.2. What is mean turnaround, normalized turnaround time? Okay, fine. So I just believe in you that whatever calculation you have done, it is correct. Fine. So you understood the idea. You understood the idea. Okay. So that is one exercise. The second exercise, you just note down this and you can do it afterwards. Okay. You can take a screenshot for this and you can do it afterwards. Next is round robin. Next strategy is round robin. This is easiest way to reduce penalty that short processes suffer with Fcfs is to use clock-based preemption. Now, from non-preemptive Fcfs, we are moving to another strategy called round robin, which is preemptive strategy. And it is clock-based preemption. I told you that preemption can be again at, of different types because of which reason preemption is happening. So that is different types of preemption. So one of the preemption is clock-based preemption. Okay, and this is again very easy to understand, this idea. It is also known as time slicing because each process is given a slice of time before being preempted. It is very simple idea. The idea is like this. There is a queue of the ready processes. A process will run for certain amount of time. Then it will be preempted and it will again join ready queue and another process will run. And another process will run. Again, it will run for the same amount of time. Then third process will run and that will join ready queue again. Okay. So can you think of any real world example where you have seen this kind of strategy? Tournaments where it is based on time. Which tournament is based on time? Chess. Chess, again, it is of different types, right? I mean, I'm not much sure at international level how this timings are measured and what basis. But here, every person gets the same amount of time. Every process will get the same amount of time. Okay. So let us think about some other example, real world example where this round robin is used. Can we think about some other real world example where round robin idea is used? I'm not able to right now recollect any such idea. It is a case where there is only one resource and multiple people want to use that. But then let's say that resource is given to the first person and ask that you can use this resource. Okay, we can consider a TV in our house. IPL again, it is not round robin. It is not round robin. Okay. Student present in this session mentioned their roll number for attendance. No, it can't be considered as round robin because everyone is sending their answer. It depends when it comes on the system, right? It is not like that. Okay, that everyone gets the same amount of time to present their answer. It is again not round robin. We can consider the use of TV in the house. Maybe let's say there are few members in the house, and everyone gets the same amount of time to watch their favorite program on the TV, and then after remote should be given to some other person. Maybe that is the close one to that. Okay, what exactly happens in round robin? So clock interrupt is generated at periodic intervals. We know that there is some interrupt which is generated periodically, and when an interrupt occurs, the currently running process is placed in the ready queue. Basically, this interrupt is nothing but the alarm that is telling that your time is over and you need to go back to the ready queue and next process will run. So something like that. And next ready job is selected on FIFO basis. So you can see this is also one type of FCFS, but it is preemptive FCFS, right? It is one kind of preemptive FCFS. Now, the time which is given, the time amount which is given to every process to execute on the processor, that is called time slice, or it is called quantum. It is also called quantum, and in short we call it Q. So let us see one example, the same example that we just discussed for FCFS, the same example we'll discuss with round robin, where time quantum which is used is of length 4. The time quantum length is 4. It means every process will get 4 unit of time to execute. So let us see the same example. Okay, the example is same. Let's see what happens. At time 0, there is only one process. Okay, and it has total 4 unit of time, but it requires only 3 unit of time. So at time 3, A will be completed, and now there is only one process B in the queue. Currently there is only one process in the queue, which is B, and B requires 6 unit of time to be completed. So tell me, what will be the next step here? At which time? The next step I'll show here. B starts at 3 and it gets total 4 unit of time. So at t equal to 7, correct? Now there are 3 processes. Can you see this order now? Why C is here, D afterwards, and B is last? Because B was executing when C and D came. Because C and D came at time respective time 4 and 6. So C came first, then D came, and B, which executed just now for 4 unit of time, it is still not completed. So it will be preempted and it will join this queue again at the end. So now at time 7, C will be executed next. So what will be the next step? At which time we will see the next step? At 11, correct? And while at 11 C completed, D is the next process, B is already after that, and E came at 8. At 8, E came. So this is the current scenario. So D will execute next. And what will be the next step? At 15. And what will be the order in the queue? At 15, what will be the order? BED. Okay, DEB. Fine. Both you are going in from reverse. Fine. So that is, if we go from left to right, it is DEB. So B is at the start. Correct. Now, next step. At which time we will see the next step? Not 19. No. Because how much service time is still left in B? How much time it has to execute for 2 units? 4 units already executed, only 2 units are left. So at 17 you will see the next step, because B will be completed at 17, because it has already executed for 4 units and only 2 units are left. So at 17 now process will be switched. Now E will go next. So what will be the next time unit? At 19, correct, because E requires only 2 units. And when this D will be completed, it has already executed once. At 20 it will be completed, and at 20 your queue will be empty. Your queue will be empty. Does this make sense to everyone? So you can see that A started at 0, completed at 3. B started at 3. It was preempted at 7. Then C started and it was completed because it requires only 4 units. So it was completed at 11. D started at 11 and preempted at 15. B resumed at 15 and completed at 17. E started at 17 and completed at 19. And finally, D resumed at 19 and completed at 20. So can you find out all those quantities for this? That is turnaround time for each process, finish time for each process, turnaround time for each process, and normalized turnaround time for each process, and then mean values. Can you do it very quickly? I'm waiting for your answer. Yes. What are the finish times? They are very simple here. Three, 17, 11, 20, 19. Okay, correct. These are the finish time, turnaround time. Turnaround time is also very simple to calculate. It will become 3, 15, 7, 14, and 11, correct? Normalized turnaround time. 3 by 3, 1, 15 by 6, that is 2.5. Then 7 by 4, that is around 1 point, how much? 1.75. Then 14 by 5, that is almost 3, right? That is 2.8 actually. 14 by 5, I guess it is 2.8. How much? Yeah, 2.8. And 11 by 2, that is 5.5, correct. So that is normalized turnaround time. And what are the mean turnaround and mean normalized turnaround? Mean turnaround time would be 18, 25, 25, 20, 50, 50 by 5, 10. Is it 10? Mean turnaround time, is it 10? So these are the turnaround times. That is correct. Mean normalized turnaround time is 2.71. Okay, fine. And the same example with Q equal to 1. Now, can you do it very quickly? Q equal to 1, very quickly. We don't have much time. We need to complete this round robin and the next one also. Now, from Q equal to 4, we are moving to Q equal to 1. So let me show it here. So if you use Q equal to 1, this is the case. Just go through this very quickly, and if you have any question, you can ask. The time quantum is 1. So every 1 unit, after every 1 unit, it will check. I mean, it will switch the process if required. I mean, if there is any other process waiting, then it will be switched. So these are the turnaround times now for the same process set when Q equal to 1. Okay. And now if you compare this quantities of finish time, turnaround time, and normalized turnaround time when Q equal to 1 and Q equal to 4, what it says. So mean turnaround, normalized turnaround time is same. Mean turnaround time in case of Q equal to 4, it is better, little bit better. Okay, but again, these are very small example. Okay, but if you compare them, still Q equal to 4 is better, isn't it? Q equal to 4 is better. Can we say that way? If you compare process by process also, except this one process, or for all other process, normalized turnaround time is better, except this last process. So no, OS does not calculate it, but it has to be predefined. Again, this round robin is not used in its pure form in modern day OS. In case of Linux, actually there are scheduling used at user level and kernel level, and at kernel level round robin is used. We will see that. Mainly in Unix, feedback queue is used. That is what we will be looking at in the next lecture. Okay, so the strategies that we are learning right now, not necessary that these strategies are used in the same way that we are discussing here in the actual OS. Maybe they are used in some hybrid form. Okay. So again, let me remind you one more time that whatever we are discussing, that is the general idea. It may not be exactly being used in the modern day operating systems. And someone asked that whether this round robin time slice, whether that value is predefined or OS calculates. So it depends how OS has implemented it. It is possible that it was predefined, but with the running average of process, I mean running the service time required for running average of the service time required for every process, it may be getting changed. That is also possible. So it all depends how OS is actually implemented. So we can't say anything right now with confirmation that, okay, it is happening this way only, until unless we refer the document of that operating system. Does that answer your question? Okay. Now there are some issues that we need to discuss with round robin. Length of the time quantum. How to decide the length of the time quantum? Suppose if time quantum is very short, so in that case, short processes move very quickly. Okay. What it says, if time quantum is short, then short processes will be completed quickly because they are, they require less service time. But long processes, as they are at one moment, at one particular time, they get very small amount of time to be completed. So they need to go from running to ready state and ready to running state very frequently. I mean, for so many times it has to go through that. So short processes will be completed quickly, but not long processes, and it will increase the processing overhead, because so many times process which happen as time quantum is very short, very quickly process will be switched. So there will be some overhead for that, and hence very short value should be avoided, and that's why we should not use very short value. But let's say if time quantum is very long, if it is very long, then long processes will get more time to run and it will degenerate to Fcfs. So it will be very similar to Fcfs. Do you agree with this sentence? If time quantum is very long, let us say the longest process in the system, requires, let's say, 10 unit of time. And if your time quantum is 10, don't you think that it will become simply Fcfs? Because every process will be completed and then only it will be going, right? So then what is the ideal value of time quantum? It should be slightly greater than the time required for a typical process interaction. Now, what is that? Okay, slightly greater than the time required for a typical process interaction. Let us try to understand. I think we have that. Fine. What it says, what is process interaction time? Basically, the time required for process to complete, that is process interaction time. Okay, and it should be slightly greater than that. But again, as I told you, this is not simple to decide. It can be changed dynamically, because while keeping the moving average or running average of the service time required, you may change this quantum value. Another issue, one issue is to decide length of the time quantum. That is one issue. Another issue is relative treatment. Now, what is that? Another issue with round robin is relative treatment for CPU and IO bound processes. So if you remember, Fcfs was favoring CPU bound processes. What happens in case of this? If there is a mix of CPU and IO bound processes, IO bound process would run for short time and soon block for IO and goes to block queue. So same thing is happening. CPU bound processes would utilize entire time quantum and returns to ready queue. So hence IO bound processes would have poor performance. So basically the same problem that we had in case of FCFS, the same problem remains here, because ultimately what you are doing, this round robin is also one type of FCFS with some preemption. Now, if you can think about this, that round robin is also using FCFS internally with preemption. But ultimately what happens? Ultimately what happens that CPU bound processes is using more and more processor time, while IO bound processes, they have poor performance. Do you agree with this statement? Can you visualize this? Yes, can you visualize this? Why IO bound process would have poor performance? Because what happens as soon as they get chance to run, very quickly they become blocked, they will be blocked. But as soon as they become blocked, very quickly again they will be ready, because whatever they are waiting for, let's say it is available and they become ready. But even after becoming ready, they will join the ready queue at the end. So whatever processes are there before it, they will go through that processor first, and then this will get the chance. But again, as soon as this IO bound process gets next chance, again it will execute for a very small amount of time. It may not complete the time quantum, and again it will get blocked for some IO, because that is IO bound process which is waiting most of its time in IO. So in that case also, most of the processor time will be utilized by CPU bound process, and IO bound process would have poor performance. Poor performance means it will be delayed. Are you getting this? Okay, so what can be the solution to this problem? Because FCFS is also favoring CPU bound process, round robin is also favoring CPU bound process, or it is also giving better performance for CPU bound process. So what can be the solution? Round robin looks nice. It looks nice that it is not allowing to process to monopolizing the processor. It looks nice because it is preemption based method. So can we find some solution with the keeping this round robin idea in the center? Because what is the problem here? Time quantum, again, that is not in our hand. Time quantum can be decided differently. Can we solve this problem within round robin? Can we do something in this round robin strategy so that we can at least solve this problem up to certain extent? Any idea to solve this problem? If you have any idea, you can unmute and you can speak, no problem. Exactly. Someone has answered that IO, that is not IO, but IO bound process that is sent to block is reassigned higher priority. So basically we need to define priority, and that is virtual round robin. That is virtual round robin. So solution is to have separate queue for the processes just coming out of block state and give them preference over the process present in the ready queue. Preference or priority. Hence, there will be two set of queues, one for the preempted process, that is ready process. Okay, it has completed its time quantum and it is preempted, so it will join the ready queue. One for the processes that have just come out of IO block, and that is another queue, auxiliary queue. So when there is any process present in auxiliary queue, preference would be given to it over processes present in the ready queue. And very simple idea. This is called virtual round robin, where we have multiple queues. So just try to see this, understand this queuing diagram. This is my ready queue. If process completes its quantum, then it will join back here. But if process gets blocked in any of this IO queue, there are different IO queues for different IO event. Okay, whenever any process gets blocked, it will join corresponding IO queue. But when that process will be unblocked from any of these IO queue, it will join another queue. This is auxiliary queue. So now when it is time for dispatcher to select next process,
either from ready queue or auxiliary queue, it will give priority to the processes which are there in auxiliary queue, because auxiliary queue holds those processes which are kind of IO bound processes, and those processes which were blocked and could not complete their time quantum, so they will be given higher priority. Does this make sense? Does this make sense, virtual round robin? So this was the one solution given by some researcher. So now do this exercise. Take this screenshot and do it quickly for q equal to 2 and q equal to 4. Have you noted down this question? Yes. Okay. Next is shortest process next. Next is shortest process next. Okay. In some literature, it is also called SJF, shortest job first. So both are same, shortest process next or shortest job first. In some literature, it is called shortest job first. It is non-preemptive policy, first of all. Non-preemptive. Once scheduled, once it is executed, it will not be preempted. Process with shortest expected processing time is selected next. Now this is interesting. Process with shortest expected processing time. Now here it means process, for every process, what is the processing time required, that should be expected, that should be calculated. Short process jumps ahead of longer processes. Another method to reduce bias in favor of long processes inherent in FCFS. This is another method to reduce the FCFS bias for the long processes, because FCFS favors long processes. Okay. So same example, let us understand this example. What happens at time 0? There is only one process A, so it will execute. Okay, and this is non-preemptive. Remember, once process is scheduled, once it is executing, it will be, it is not going to release the processor until unless it completes or blocks. And here we do not consider any IO. Okay, so we don't consider any blocking stage. So at time equal to 0, A will be scheduled and it will be executing for 3 time unit. So at t equal to 3, B has already arrived. So that will be scheduled and it will complete after 6 time unit. So at t equal to 9, now you have all these 3 processes came in this order. C came first, then D came, and then E came. Now you see the arrow, where the arrow is. Where the arrow in this? E, YE. Because at time 9, when it evaluate which process has shortest process next, I mean, which fits in this strategy, shortest process next. So which process requires shortest amount of time? E. That requires only 2. Out of these 3, E requires less amount of time. So E will be scheduled next. So E will execute next. It will start execution at 9. It requires 2 time service unit, 2 time unit for to service it. So at 11, is there any mistake? I guess yes, because it requires only 2 time unit, right? It requires only, so this should be 11, isn't it? Right? So there is some mistake in writing this. So this should be 11. At 11 now it will be again decided between C and D. So between C and D, C requires less time. So 11 plus 4. Okay, maybe that's the problem. Okay, but at 11 C will be executed and it will be executed for 4 time units. So at 15 this should be actually 15, right? This should be 15. I'll change this. So at 15 now D will be starting executing and at 20 it will be completed. So this is SPN, shortest process next. This is the SPN. Does this make sense? Okay, and if you find out this finish time, turnaround time, and normalized turnaround time, so you can see it is better than round robin of Q equal to 4 and Q equal to 1. Is it? Is it better than that? Yes, it is better than that, right? What are the issues with SPN? Let us quickly go through this slide. Difficulty associated with SPN is the need to know or estimate required processing time for each process. Okay, you need to estimate how much time is still left, how much time is, or rather how much time is required. In fact, that is the need for any such strategy. Service time needs to be known prior to starting, because in every example we have considered that column called service time, and that needs to be estimated, and that is the difficulty with actually all such strategies. In case of batch jobs, now we have two types of system, batch job system and interactive system. So in case of batch jobs, programmer can estimate the value for time. You can estimate that time, that okay, this particular job will take this much amount of time. In case of batch jobs, if estimated time for process not correct, the operating system may abort it. That is also possible. For interactive processes, the OS can keep. Now this is interesting because in interactive process, it is the most difficult thing to estimate how much time will be required by this process. Can you estimate that? Come on. For interactive process, you can't estimate how much time this process will require to complete its job, because it all depends on IO when it is becoming available, when user is providing some input. So in interactive processes, it is the most difficult job. The OS can keep a running average of for each process. So that is one possibility. How to estimate this required time, required service time based on this running average of each process. Other approach is to gather the statistics if the same job runs frequently. You may assume that, okay, if this job has already run before and it took this much amount of time, this time also it is going to take that similar amount of time. But in all this case, possibility of starvation for longer processes is there. Okay, can you justify this statement? With SPN, that is shortest process next, there is the possibility of starvation for longer processes. Is it justifiable? Is this justifiable? Possibility of starvation for longer process? Okay, fine. I think you need to go for the next lecture. So let me stop it here and we will continue from this point in the next lecture.